Hi everyone, in today's video I wanted to dive a bit deeper into the group relative policy optimization algorithm. It's at the center of the newest DeepSeek R1 paper and DeepSeek Math and all of these. It's not that complicated, but you kind of need to walk through it slowly in order to understand it properly. And also find some code from HuggingFace. So they are working overtime to get this into their trainer. So we're going to go through their code base and then actually look at the implementation and how it differs slightly from the actual formula. So we're over here. If you watched the previous video, you're already familiar with this map. I'm just going to recap it quickly. So here, this is where the DeepSeek R1 start, right? We have DeepSeek V3 base, and this is where it ends. You have DeepSeek R1 0, the distilled version of DeepSeek R1, and then you have DeepSeek R1 over there. So the group relative policy optimization algorithm appear here mainly in the DeepSeek R1 0 path. It's different from the previous algorithm that was used for reinforcement learning from human feedback, which is PPO. So we're going to quickly go and check out like the difference in the formulas. So most of the information I'm going to show you doesn't come from DeepSeek R1, it comes from DeepSeek Math. This was published a while ago. Here we are, we have the PPO algorithm, which is the classical one that was used for reinforcement learning from human feedback. And then we have the difference with the GRPO. The PPO algorithm, I highly recommend this video, right? Proximal policy optimization, PPO, how to train large language module from Cyrano. Absolutely awesome. Like it goes very slowly, step by step in each of the step of the algorithm. So in PPO, you have two models. You have the value model and then the policy model. And then in a nutshell, the value model is like, what are the values for each of the place in the grid, each of the states that you're at in. And then the policy model is like at each of the states, like what's the probability that you should go in whatever direction. So you train these two things in parallel using the gain, which is like the difference between what you said it was and what it actually was. So that's kind of the idea. What GRPO is saying is that you kind of don't need the value model and we can bypass that and then just use the policy model to approximate the advantage and we should be good to go. If you take a look here, the value model is going to output the value. And then these value through the generalized advantage estimation over here will generate what we call an advantage, which is like some sort of normalized reward here that will get fed back to the policy model. It's kind of what's up in the PPO world. In the GRPO world, there's no value model. There's just like the policy model. And then this whole section for the reward has been removed and replaced by group computation, which basically means that the policy model, instead of just outputting one output for one question, right, it will output multiple ones. With these multiple output, it will generate multiple reward, and then you're going to get multiple advantage, which will be used to optimize the policy model. So you kind of bypass the need for a value model. So in GRPO, you still keep the same two model for the reference and the reward model as a PPO. It's the value model that is gone. A reference model is in the paper, they are saying it's a DeepSeek V3 base model. So like this one over there, right? In the algorithm that they show, it's not exactly that. It's like optimized old model after a while. Yeah, anyway, and you keep the reward model over here, and the reward model can be a neural network, but it can also just be like some rule-based thing. And in our case, for this paper, it was some rule-based reward functions. And as we're going to see in the code, it's also a bunch of reward function that we have. That's at the high level. The interesting two bits of information, right? In this PPO, look at where the KL divergence is. It's like near the reward side, right? And in our case here, it's not there. It's near it's outside of the reward. So we'll see this slight difference in the formula. So if we look at the PPO, what you're trying to do is you're trying to maximize this objective, which is a big formula. It's fairly verbose, but like if you look at this map, it's not that complicated. Like O is your output, Q is your question, R is the reward, A is the advantage term, which is calculated in a specific way. So you're trying to do the mean of like all of the output that you're shooting out there, right? And then you're gonna clip the amount of change that you can have in a particular step, right? So like you have here the P with P at theta for like a specific like output that you have for a specific question. And in this case, this is the model that we're like actively modifying. And this is the previous iteration model. So why we're doing this divided by the previous model is to kind of have a sort of momentum, a bit like with Adam and like these type of optimizer. It's a very different, but like it's the same kind of rough idea. So if you're like been decreasing, you're gonna decrease faster, and if you have been decreasing and then now like you're increasing, right? This like probabilities, you're gonna increase a bit lesser. That's kind of the rough idea. So this is how confident are you from your output, and then this is like your reward, like how much are they worth really. And it's a normalized one. And then we're doing like the minimum between this quantity and this quantity, because in this quantity we don't want to take too big of a step. So if you are above a certain epsilon in any direction, right? So like if you were saying the limit are there, right? And then like you were there previously, so you're only allowed to change like the parameters a bit over here and a bit over there. So if for some reason you're like going crazy and you're trying to put the parameters like way down or way up, it's gonna clip it, and then you're just gonna bring it all the way back to the minimum that you have over here. That's a rough idea here. It's just to avoid like a very erratic movement. So the A here is like the advantage, and it's gained through like this generalized advantage estimation. The reward is normalized with this term, which is the KL divergence term. The KL divergence, like we saw in the previous video, is like the difference between two distribution, right? And in this case, it's the difference between the ref distribution, the ref parameters, and then the current parameters that we have. The ref here is the DeepSeek V3 base model, and we're gonna see in the algorithm it's not always that, but here they're saying the ref is the reference model, which is usually the initial supervised fine-tuning model, and base the coefficient of the KL penalty. So you have like these hyperparameter also. In a nutshell, this is PPO. So the change that they did, right? If you look here, they're gonna move this KL divergence thing here to the reference model, but like in not with the reward. And then they're gonna remove that part and that part to just have a group computation. So there's gonna be a bit more averages in there. So if we look at the formula, it's this similar thing, right? Don't freak out. It's exactly the similar thing. There's this different groups. So we're doing like an average of the groups that we're gonna output. And the groups is just like a bunch of output for one given question that you're getting there, right? So here, this is a group. So you have one question, many output. So 1, 2, G. Right, and this is for all of the output that you're having, and then you're doing the same thing, you're minimizing. So this we know, this is the clipped thing, this is like the same thing, it's the same thing as before, right? The KL divergence is now here, right? And we're doing minus this because we're maximizing this formula. So it's important to keep track of the maximization versus minimization thing, because usually when it's implemented, you're trying to like have a loss out of it. So you're gonna have to flip some things in the code, but in this case, it's maximizing this formula, right? So you have a minus on the KL divergence here. You have the same story. You have the current parameters, and then the ref, which is the DeepSeek V3 base with the supervised fine tuning. And here they change a bit the formulation, and they are following Schulman over here with this unbiased estimator. So it's this thing, and then you have minus log of this minus 1. In the actual code, it will be a bit different. There's going to be an exponent that we're going to like have to go through to. It's a bit simpler to look at because there's not the logarit in there, but it's a bit different. It's not the exact same formulation. The A here doesn't go through the generalized advantage estimator, right? It's just a formula straight up. So the formula for the A is the following. It's like a normalized kind of a reward. So you have the reward at the current point minus the mean of like the group divided by the standard deviation of the group. So basically the advantage is like how much this reward is good with respect to the whole bunch of output that we have. Is it much better than the group, or like the same as the group, or like lower than the group? So if we take a look at the overview of like this whole GRPO thing, you have the prompt over there, which is your input. And this is your completion that you are gonna put out there. And then based on the completion, you're gonna output some reward. And the reward is taking a bunch of functions. And then like with these, you're taking the normalized reward over this group. And then you get what we call the advantage. And you do the same thing over here. And then you like sum all of the advantage together. And you have this side that is fixed up. Then what you have is like the calculation for the KL divergence. You have your current policy, you have the reference policy, which is like way back, and then you're trying to like calculate the KL divergence between this and that, and then this is used to how's it like you're subtracting this from like your motion that you're going through with your advantage, and then you calculate the mean, and then you have like the objective that you're trying to optimize. So that's a good overview of the whole thing. So take note of completion, prompt, reward, advantage, KL divergence. These terms will come back into the code. If we look at the actual pseudocode from the DeepSeek Math paper, you have like this setup, this 12-step. So you have the initialization of the policy model from like the first base model that you have. And then you're doing multiple iteration, and in each iteration, the ref is changing a bit, right? This is in like this pseudocode, but it doesn't match exactly the rest of the paper. So I'm not sure if this is right, or if like this init is actually like the actual base. But yeah, there's a ref which is limiting the amount of changes that you can have with the model as it goes through the multiple optimization step. Anyway. So you have that, and then this is the step that you're doing in each of the iteration. You sample a batch of data, and then you try to update the old policy model with like this one, right? The new one that you have. So in each of the step, the old policy will change. So it's like a different checkpoint, right? You have the ref that is all the way there, and then you have your old that is over here, right? And then you have your current that you're trying to modify in this current step. So the distance between these two is like one step, right? And then distance between these two is like M step. This is what they're saying in this pseudocode, right? Okay, so this is what we have. And then we sample G output from one question, right? For each question in the data set, for one question, you have a group. And then what we do is we can compute the reward like we saw. And then with the reward, we can compute like the advantage for like each of the tokens. So with the group relative advantage estimation, this formula that we saw. And then here we're doing the GRPO optimization step. So update the policy model P of theta by maximizing the GRPO objective, and then you iterate on this. And that's it. That's the, in a nutshell, this is what every terms mean in this thing. I suggest you check out like the PPO algorithm. If you understand the PPO, the GRPO is simpler. So let's jump into the code from HuggingFace now. The code is all open source, so we can take a look at everything. And like their thing is the GRPO Trainer. It's still in active development. You can still use it, but that's what they have put out there. Great work to the team. And how you use it is like this. So you import GRPO Trainer from TRL, and then this is their API. You decide which like base model you want to use to be able to do the GRPO or reinforcement learning training on it. And then you tell it what reward function you want. Let's dive into the code in a few. Before that, let's look at like their loss that they're gonna use in the GRPO training regiment. So this is what they decide to use. And here, watch out, they're using loss, not an objecting function that they're trying to maximize. They're trying to minimize the loss. So you have to flip a bunch of numbers. So basically just put the minus in front and you should be good to go. There's two things that they change. Here you see you have the old that you're supposed to keep in memory, but instead of that, they can just like slap a no grad to one of the variable and it should be good to go. So this is the same thing as old. And over here, in this one, they have a clip because they say in the original paper, the formulation is generalized to account for multiple updates after each generation by leveraging the clip surrogate objective. What they're saying is that in TRL, we only do one update per generation, so we can omit and simplify the loss to the first form, so not to have this form over here. So this is actually what we're gonna see in the paper. Second thing is that in the paper, it's probabilities, right? Now we're dealing mostly with log probabilities, right? So log probabilities, this is what you're going to see in most of the scientific packages that has to deal with that, because it's just faster, more accurate, it's simple. Log probabilities is much easier to work with than directly having the probabilities. So keep that in mind, because this will change the formulation in the code. So if we dive deeper into the code, our entry point is prediction step. There's this function, prepare input, that is doing a lot of heavy lifting. We're going to see it in a few. Where we're actually doing GRPO is here in the self-compute loss thing, right? And then we're taking the mean of that and we're returning the mean loss over there. So if you go into compute loss, this is the main like GRPO thing. We are doing a bunch of setup over there, and after that we're getting our per token log probabilities with this function over there in here. And this function, the only point of it is to get the per token log probabilities and return them to the main GRPO function. So we're doing this over there, token by token. We get the token log prob, we append it to our nice list over here, and then we're returning it as a tensor. That's very important. So at this point in time, every log PS that you're seeing is a log probability. So it will change the information that we have in our formula. Step one, KL divergence. So we have our two things. We have our current log prob and our reference log prob that was in memory. And we're doing this formula. So it's exponent of ref minus current minus ref minus current. You have to see it with the logs in it. So let's go and do the change from here to the other thing and see what we need to change in the formula in order to retain the same thing. So what I mean by that is that at this point in time, we don't have this. We have log of this, right? Log of ref, right? Divided by log of theta minus log of ref divided by log of theta minus 1. What you want to do here is to reverse this log and then simplify the formula so you have one thing to do. So here you're putting e to the log, right? Same thing here, e to the log, and same thing over there, e to the log and e to the log. And now with the property that we have over there, we can play around it a bit. So when you have e and e to something, you can do the following. You can do e to the log ref minus log theta, right? So this is good. This is exactly what we see over there, right? You see e to the log ref minus log theta. And over there, what we have is we're gonna have minus, and then this we can simplify it like this: log of e to the log ref, right? And then minus e to to log e to the log theta minus 1. Perfect. Now we can simplify a bunch of stuff. So we're going to use that one over here. So we're going to do a minus, and then we're going to take this. We're going to have log ref, right, in here, times log, when I say log, I mean ln, right? And then here minus the same thing, theta, well, log theta times log of e again, right? Minus 1. So these one, they become a 1. This one become a 1. So what you end up with is minus log ref minus log theta minus 1. Voila. So if you look back, here we have minus log ref minus log theta. Okay, minus 1. And after that, we get our magically or advantage that is over here. This advantage comes from the prepare input. So we're going to see it in a few. But after that, what we're doing is the same thing that we need to do with the token loss time advantage over there, right? These, we don't have that. We have log of the theta divided by the log of old. And then we're just taking the E over there. So we're doing E, and then it's going to be log theta minus log of old. Like this, time the advantage. Advantage doesn't change. And then here we're doing our minus, right? So we're doing minus all of this, and it's minus this bit that we just did, right? Minus that. And after that, we're kind of done. So the only thing that is left to do is this last part over here with these two. This one, and then that one. So that one is happening, the internal one is happening here, right? And then the other one is happening there, like this with the mean. So this one and that one. And if you see, there's a completion mask that is popped up out of nowhere. So this completion mask is a binary mask. So we have 0 and 1s. And what it means is that a 0, it's when you're at before the end of sequence, so in the prompt technically. And 1 is when you're out of this. So you should take into consideration only the things that are out of that. So we're calculating the loss over everything, right? But we should only take into consideration the things that are after the end of sequence. We're going to see that in a few in the prepare input. So here we are. We don't need to go into like much in here. What we need to check out mainly is the completion mask over there, right? We calculate the sequence in this and everything. And here we're trying to mask everything after the first end of sequence token. So this is where the binary mask comes from. We're using the end of sequence indices to mask the right stuff. And we're creating our 0 and 1 mask over here. So that's perfect. Now, if we go back to the reward, so this part is where like the reward things are happening, right? The reward, you should think of them is like you have a block and then you're shoving your output through that block and it will return you a reward directly. So the rewards function are these blocks over there, right? Each of these are a reward function, and then you're going to take like this normalization to get the advantage for each of them. If we look over here, we're going to iterate, and this is where we're going to call our reward function with our prompt, completion, whatever the argument that is needed, you put it there, and you get your output reward. You like stack them up, and then you're going to be able to calculate your mean group reward, your mean standard deviation reward, and then you're going to be doing our R, which is the reward, minus the mean group with reward, divided by the standard deviation plus an epsilon to not divide by 0. So the reward, you can customize them if you want to. So you can like create your own reward function like we saw at the top. Let's say here for rewarding longer completion. You can have another one with specific format and you're using regex in there, and or a reward here for complexion based on the reference or something like that. You can put anything that match your the specific behavior that you want your model to do reinforcement learning on. And that's this. After that, it's mainly just logging, and we're done. So that's it. So this is the whole thing. So if you understand PPO, GRPO makes a lot of sense. So strongly recommend the previous video that I'll be linking to the description. I hope this was useful to see a bit the breakdown in the code base and the difference that we have between what's in the paper versus the actual implementation. If you have any questions, don't hesitate to leave a comment. I'm here to help, and I wish you all a great week.